Hello everyone, myself this is Nandini from BSc MPCS. Today we are going to discuss about unit junction transistor and silicon control rectifier. Unit junction transistor. In UJT there are subtopics: introduction, construction, symbolic representation, working and VI characteristics. First, introduction. A unit junction transistor UJT is a three-terminal semiconductor switching device. This device has a unique characteristics that when it is triggered, the emitter current increases regeneratively until it is limited by emitter power supply. Due to these characteristics, the unit junction transistor can be employed in a variety of applications. For example, switching, pulse generator, sawtooth generator, etc. UJT has only one PN junction. In the image, we can observe that the UJT has three terminals: emitter, base, and collector. There are two types of UJT, which is PNP and NPN. Next, construction. Here figure shows the basic structure and symbol of UJT. It consists of a N-type silicon bar with an electrical connection on each end. The leads to these connections are called base leads, which are base 1, B1 and base 2, B2. Part away along the bar between the two bases nearer to B2 than B1. A PN emitter is lead E. Since the device has only one PN junction and three leads, it is commonly called a unit junction transistor with only one PN junction. The device is really a form of a diode because the two base terminals are taken from one section of the diode. This device is called double based diode. The emitter is heavily doped, having many holes. The N region, however, is slightly doped. Hence, the resistance between the base terminals is very high when emitter lead is open. Next, the symbolic representation of unit junction transistor. Here the image represents the symbol of UJT. It has three terminals. The three terminals of UJT are emitter, base 1 and base 2. Next, equivalent circuit of a unit junction transistor. Here the diode D represents PN junction, interbase resistance between B2 and B1. RBB is equal to RB1 plus RB2 when emitter current is equal to 0. RB1 greater than RB2 and RB1 is greater, and variable resistor which depends on the bias voltage. Intrinsic standoff ratio. With emitter open, if voltage VBB is applied between B2 and B1, then part of VBB is dropped over RB1 and RB2. The voltage drop across RB1 is VB1, where VB1 is equal to VBB of RB1 by RB1 plus RB2. VB1 is equal to VBB, where beta is equal to RB1 by RB1 plus RBB. This is called intrinsic standoff ratio. This diode is ranges from 0.5 to 0.75. VB1 reverse biases the PN junction and the emitter current is cut off. Next, the operation of UJT. With emitter terminal open, only VBB is applied between B1 and B2. VB1 reverse biases the PN junction and IE is cut off. Due to minority carriers, there is a small leakage of current flowing from B2 to emitter. When a positive voltage VE is applied to emitter, if VE exceeds VB1 by at least 0.7 volts, then the diode becomes forward biased. Then holes are injected into N-type bar. These holes are repelled by B2 and attracted by B1. This reduces the resistance RB1 and increases IE. VE increases the IE, which in turn reduces the RB1. This causes further increase in IE regeneratively. It is limited by VE. VP is equal to NBBB plus VD, where VD is equal to cut-in voltage of diode 0.7 volts. When negative voltage is applied to the emitter, PN junction is reverse biased and IE is cut off and UJT is in off condition. Characteristics of UJT. In UJT there are three regions: cutoff region, negative resistance region, saturation region. If VE less than VP, the emitter is reverse biased. There is a small leakage current and UJT is in off condition. The region left of the peak point is called cutoff region. If VE greater than VP, the diode is forward biased. It increases the IE and decreases RB1, thereby decreasing VE. IE increases until it is reached the valley point. The region between P and V is the negative resistance region. After the valley point, the device driven into saturation region. Unique characteristics of UJT. When UJT is triggered by VE, IE increases regeneratively until it is limited by VE. That is negative resistance property. The applications of UJT are switching circuits, UJT relaxation oscillator, sawtooth generator, pulse generator, timing and trigger control circuits. Next we are going to discuss about silicon control rectifier. It is also known as SCR. The subtopics of SCR are introduction, symbolic representation, construction, operation of silicon control rectifier, VI characteristics and applications. First we are going to discuss about introduction. A silicon control rectifier is a semiconductor device that acts as a true electronic switch. It can change alternating current into direct current, and at the same time it can control the amount of power fed to the load. Thus silicon control rectifier combines the feature of a rectifier and a transistor. Here the images represents the symbol and symbolic representation of the SCR. It has three terminals: anode, gate and cathode. Next, construction. Here the figure shows the construction of the silicon control rectifier. Silicon control rectifier is having 4 layer, 3 terminals and PN semiconductor device. It has 3 junctions where J1, J2 and J3, and since it conducts only in one direction, then it is known as unidirectional device. It is called as control rectifier because this device requires a gate signal to turn it on, and it can also used as rectifying diode. Here in the image we can observe that the construction of a SCR structure. It has 3 terminals: anode, gate, cathode, and it has three junctions: J1, J2, J3. Operations of SCR. In silicon control rectifier, the load is connected in series with anode. The anode is always kept at positive potential with respect to cathode. The working of silicon control rectifier can be studied in two ways. The two ways are when gate is open and when gate is positive with respect to cathode. First we are going to discuss when gate is open. First condition. In the image it shows the SCR and a silicon control rectifier circuit with gate open, that is no voltage applied to the gate. Under these conditions, junction J2 is reverse biased while junctions J1, J3 are forward biased. Hence the situation in the junctions J1 and J3 is just as in NPN transistor with base open. Consequently, no current flows through the load RL and SCR is cut off. However, if the applied voltage is gradually increased, a stage is reached when reverse biased junction J2 breaks down. The SCR now conducts heavily and is said to be in on state. The applied voltage at which silicon control rectifier conducts heavily without gate voltage is called breakover voltage. When gate is the next condition, when gate is positive with respect to cathode, the silicon control rectifier can be made to conduct heavily at smaller applied voltage by applying a small positive potential to the gate as shown in figure. Now junction J3 is forward biased and the junction J2 is reverse biased. The electrons from N-type material start moving across junction J3 towards left, whereas holes from p-types towards the right. Consequently, the electrons from J3 are attracted across junction J2 and gate current starts flowing. As soon as the gate current started flowing, anode current increases. The increased anode current in turn makes more electrons available at junction J2. This process continues and in an extremely small time, junction J2 breaks down and the SCR starts conducting heavily. Once SCR starts conducting, the gate loses all its control. Even if gate voltage is removed, the anode current does not decreases at all. The only way to stop conduction is to reduce the applied voltage to zero. The VI characteristics of silicon control rectifier. Here image represents the VI characteristics. Figure shows the VI characteristics of a SCR, which is a curve between anode cathode voltage and anode current I of a SCR at constant gate current I of an of an SCR at constant gate current. Forward characteristics. When anode is, there are two types of characteristics in SCR: forward characteristics and reverse characteristics. First, forward characteristics. When anode is positive with respect to cathode, the curve between voltage and current is called the forward characteristics. Here the OABC is forward characteristics of silicon control rectifier when gate current is equal to 0. If the supply voltage is increased from 0, a point is reached when the SCR starts conducting. Under these conditions, the voltage across SCR suddenly drops as shown by the dotted curve AB, and most of supply voltage appears across the load resistance RL. If proper gate current is made to flow, SCR can close at much smaller supply voltage. Then reverse characteristics. When anode is negative with respect to cathode, the current between voltage and current is known as reverse characteristics. The reverse voltage does come across SCR when it is operated with AC supply, means alternate current supply. If the reverse voltage is gradually increased, at first the anode current remains small, and at some reverse voltage, some avalanche breakdown occurs and the SCR starts conducting heavily in the reverse direction as shown by the curve DE. This maximum reverse voltage at which SCR starts conducting heavily is known as reverse breakdown voltage. From the image we can observe that there are two conditions: forward conduction region and reverse conduction region, where the upper part represents forward characteristics, where the down part represents reverse characteristics. And applications of SCR are, it can be applied in many electronic devices such as battery charge regulator, computer logic circuit, whereas inverters, over voltage protection circuits, control rectifiers, zero voltage switching circuits, power switching circuits for both alternate current and direct current. Thank you.